All right, so I made new announcements, just same money's point to this Sunday. Now that you've all got groups, so thanks for spitting those on time. Then with your groups, the next thing due Saturday is to just come up with a nature-inspired algorithm that you want to work on. Don't have to tell me what you're going to work on, like exactly how you're. I'm just looking for like a sentence. So like if it's one, I have a huge candidate list. It's one off of that. Then in this assignment, just tell me the name off that list. Show me that you've got a plan. You don't have to stick to this plan, but at least you have a backstop. And then if you decide to switch, that's fine. I don't go back and check for consistency. Just want to make sure you've got at least one ready to go. If you want to do something that's not on that list, but you think is relevant to the class, then just give me the name and then give me a little 1 or 2 sentence justification. Like, this is an algorithm that's inspired by, the way trees grow or something like that. And then, it's not on the list, but it is, the algorithm is directly inspired by a certain biological process or whatever. And then I'll just read through those and check off on those. So that's that deliverable. And then the next deliverable, which I think would be just like either a week or 2 after that, will actually be like 2 paragraphs where you'll give me your snapshot of your impression of how the algorithm works very concisely, like just in a paragraph, and then a rough sketch concisely in a paragraph of what sort of demo that you're going to do. You can say, look, I've got this data set that I've already have available for me that I'm going to train this algorithm on, or I'm going to use this algorithm to optimize gameplay in a simulated environment, or these sorts of things. And so just give me sort of an idea that you have kind of a path forward. Don't have to give me all the details, but just want to show me that you've got something to work with. But that's not this first deliverable. That's what you do after that. This weekend, I'm just looking for a name. Then there's also mini project 4. That's if the schedule goes according to plan. If things go a little too slowly this week, then I might bump that a couple of days. And then concept check 5 are due. I meant to flip that around. So I meant to say mini project 4, that is due Sunday, but concept check 5, that's if schedules go a little slower, then maybe that will get bumped a couple of days. So we'll see. All right, any questions about the deliverables and project stuff going forward? And then this is this algorithm choice, that's a group assignment. So I've added you formally to Canvas groups, and this assignment is a group assignment tied to those groups. So once one of your group members completes it, it automatically is linked to both. So not only one has to submit that. Okay, so we've now started into Unit 5. This physics by machine learning. Simulated annealing as our kind of motivating driver. So I presented it very briefly last time. We are going to then, we have to pick up a bunch of things along this unit in order for us to return to it, to have all the tools to actually understand how to implement it and what it's doing. So as a refresher, so this is a little demo of what simulated annealing looks like when it's run. You've got a fitness landscape like this one, which you can view. I said fitness, but it's an energy landscape. So the narrative here is that we're minimizing that. So the decision space is a set of microstates inside we'll say inside a macrostate. So these are microstates that are consistent with the configuration of a system, but some of them are at higher energy, so they're less likely. Some of them are at lower energy, so they're more likely. And so we use a temperature variable to move the system through its microstates, trying to get it into this lowest energy state. And so if I were to just run this with one temperature, like a high temperature, then we see that the system is going to jiggle across lots of different microstates. And because it has a lot of energy available to it, it can jump over very high peaks. So it can go from a low peak to a high peak because it's got the energy budget. It can pay that cost. But as we reduce the energy, so if I go to like a medium temperature, then it has less ability to get out of these gaps because it has less budget available to it. And so it ends up getting more stuck. And then this is even worse I don't want to say worse, but it's a stronger effect with low temperature. Once you're at low temperature, then it pretty much converges on a particular level here. Now, notice that I just happened to catch it in this deep well here. So I basically manually did an annealing process where I heated the process up. So I went to high temperature, I got the system hot so that it started exploring all of its microstates. And then once it was exploring, I slowly cooled it. And by cooling it, I was kind of lucky enough to trap it over in this area. And it started to explore just this area. And then I cooled it even more. And then I trapped it in the lowest well here. So when we finally get to simulated annealing, we'll define a way to automatically do this annealing using the so-called annealing schedule. So we'll define this way to automatically lower the temperature, and we can define the rate at which it lowers. And for certain optimization objectives, you'll need to spend more time exploring. Other optimization objectives, maybe you can jump to exploitation a little bit faster. So the key difference between simulated annealing and genetic algorithms, in genetic algorithms, we start with lots of diversity and it naturally bleeds away from us. And it is our goal in genetic algorithms to build diversity preservation mechanisms to keep that diversity as long as possible, because the more diversity you have in your genotype space, in your chromosome space, then the more exploration you get to find all of these potential fitness peaks. But then over time, the act of selection and a little bit of drift starts to reduce that diversity and you start committing to one area of the fitness landscape. Here, we fix diversity externally with temperature. And so if you set a high temperature, you're gonna move all around the space. And that's great for exploration, but we eventually need to commit. And so by fixing this annealing schedule, what we're doing is artificially imposing what genetic algorithms do automatically. So genetic algorithms actually bleed the diversity from the system. We are going to externally bleed the temperature from the system. And as we cool the system down, we force the searcher to go from exploration to exploitation. That's what we're building up to. But in order to build this, we need to know what is the best way to simulate a physical system. So rather than just coming up with an arbitrary way to search through this and kind of coming up with our own fake temperature variable, then we want to say, is there a more physics-inspired way to do things? We know that this process works. There is a such thing as annealing in real life. And so if we simulate annealing, maybe we'll have a better chance of this working out as well as it does in real physical systems where you do this temperature stuff. So that's the motivation for this unit. Any questions about this picture? Again, I'm not expecting you to understand how to build this yet. We have to build all the tools we need to bolt together to make this happen. Yeah.
Can you repeat that, please? Why do you expect that this annealing process would somehow have an advantage over what we've already gone through?
Well, so we'll speak to that a little bit today about, but the idea here is that, like with genetic algorithms, someone looked at evolution and said that if the conditions are right, evolution, if the conditions are right for natural selection to do its work, then we can see natural systems tending to have an optimization-like feel. They're a little limited, but they, at least in a self-organized way, can move from kind of poor strategies to better strategies. And so that was the inspiration. The sort of engineer looks at that and says, can I fine-tune that evolutionary process to make that work more reliably, and then use that in an optimization search? And it's the same thing here, where we know that people who work with metals, work with materials, if you need to get rid of impurities in a material, then we know that just heating that material up, we know that they have complex energy landscapes like this. And we know that if a material has impurities, then it's modeled as being in one of these local wells. And so we know that a way you get rid of impurities in a lot of these materials is by heating them up to the point where they're a little bit looser. And then when they're heated up, then there's a chance for them to find states where if then you cool them back down, you can catch them in lower energy states. And so if you look at the lattice that's making up a material, there might be these like interstitial problems where it's instead of having a nice regular pattern, there might be some like notch or hole. And if you heat them up, then you get some fluidity that allows the system to settle down into a pure state where things don't have that impurity. You had to heat them up, and you can't immediately cool them down because you heat them up and they could, you might introduce more impurities. But if you heat them up so they're fluid and then slowly cool them down, then we know that in physical materials, you can make things smoother, purer, it's a better quality material. And so the thought here is an energy landscape may as well be an optimization objective. So if I could create a fake material whose energy landscape follows my optimization objective, if I can heat it up, cool it down, then maybe I can also catch it in this global minima, which is, there's a lot of these local minima. Maybe I can manage to skip those and land here. So that's what we're trying to build. But, we know physics does it well, so we're going to try to mimic all of the aspects of what physics does, because as we'll see, bias is a big part of the thing we want to kind of get rid of when we do these methods here. And you'll see, I think, hopefully by the end of this lecture even, that a lot of the tools that you might see used over and over again in machine learning are tools that were borrowed from physics, because these physical processes that we model tend to be ones which seem to reduce the dependence on extra assumptions, in other words, extra biases. And so part of embracing physics as our inspiration is embracing a method that pushes out all of the assumptions as possible so that we have a search that is sort of as pure and unbiased as possible. That's a big, when we talk about physics inspired, that's really what we're looking for, as minimalistic and as sort of assumption free as possible. And that, I hope, will start to make sense toward the end of this lecture. So that's our motivation, that's our inspiration. So where do we go from here? Okay, so this is just in a static form, summarizing what I just was talking about on that toy there. If you would like to, so this is available on Canvas, but if you'd like to check that out, there's a short link to it as well. All right, so how do we mimic these things? So right now, we would look, so as I mentioned last time, we're going to hold our system at multiple temperatures, but when it's at a particular temperature, we need to know what distribution of perturbations are we going to allow for this microstate to move around. So if we get this distribution wrong, then we might end up generating some sort of biased search. So like it might be that we accidentally make it so the microstate tends to go left instead of going both left and right. And so in a high dimensional microstate, it's not trivial to sample or to perturb off of that microstate in ways that are beneficial. So we want to sort of say, how does physics do it? And so we, in our physical model, this is the one thing that, this is how temperature relates to our system. We set a temperature, and that temperature basically gives us an average budget for these energetic fluctuations, for the amount of change we can get from one microstate to another based on its energy. So this here is a constraint on the distribution of fluctuations, not on our individual delta E's, but it's a constraint on the distribution of our delta E's. So you can have a change in energy that's bigger than this, but it will be rare. You can have a change in energy that's smaller than this and it will be more frequent. You can have a negative change in energy and it will happen immediately. So there's no barrier to that. So our question is, what is the right search distribution? What is the right distribution of energetic perturbations? What is the right way to move our microstate around? That's what we're trying to build up to. So, we can ask, what is the distribution in nature? So if you set a chair at a particular temperature, then what determines how that temperature, it gives the chair enough energy to move from microstate to microstate. And so we have to think of how do we go about modeling the distribution of energies that we would expect in nature. So here's a thought model that we'll start with here to get us moving in this. Like, imagine if, imagine for a spatial constraint. So right now I'm focused on, this is almost like adding a new constraint to my macrostate definition. So this is the constraint that I'm focused on here. And imagine if we hold off on thinking about this constraint and instead think about a spatial constraint of particles in a box. So they're constrained to be in a box. That's all we know. There's no other constraints on them. So we want to say, if that is our only constraint, they need to be constrained to be in a box. What is the most natural microstate distribution for, let's say, 4 gas molecules in that box? Do we think that it's, this description of a macrostate, all molecules in the corner of a box, or something more like this, 1 molecule per quadrant? So both of those are reasonable ways to describe what could be in that box. But this here, you've got fewer microstates. So there are fewer ways for all 4 of those molecules to be in the corner of the box. Or in other words, if you perturb that, then you're most likely going to move out of that microstate. So it's easier to move out of that microstate than into that microstate. And so, or out of that macrostate into a different macrostate. Whereas over here, if you move one of these molecules around just a little bit, it still fits into this 1 molecule per quadrant. So now, if you cut this thing up into quadrants, you've got a lot of freedom where it is long, and then even if you swap, 1 molecule for another, you're still in the description. So there are a lot more ways to organize those molecules that fit into this 1 molecule per quadrant description than there are in this description where all molecules are in the corner of the box. So if we just look at that, then that suggests that if you choose from a random configuration of those 4 molecules, there are more options for it to be 1 molecule per quadrant than all molecules in 1 tiny corner of the box. So there's a numerosity argument here, that there's just more microstates on the right side of the page than the left side of the page. The other argument we have here is that there are more severe constraints in this description as opposed to this description over here. So if I think, all molecules in the corner of the box, I'm adding a lot of information to this macrostate is more restrictive as opposed to just 1 molecule per quadrant. So this captures the same idea as this fewer degrees of freedom, but it just says it in a different way. The macrostate has a lot more conditions on it. It's saying, a particular corner of the box, a particular radius, there's a lot that's sort of saying, what does it mean to be a corner of a box? But you have a lot more freedom when you just say the whole quadrant. So there are fewer hidden added constraints on this side here. So that's the type of thinking that we're going to develop today, is this idea that the distributions that we expect nature to be in are going to be distributions that minimize the added information beyond the system constraints or maximize the degrees of freedom or accessible microstates. And this is what we're going to define as this concept of entropy. So we're going to look for maximal entropy distributions. These are distributions that reduce the additional added assumptions or constraints that are put on the distribution through its shape. So we just want to say, we've already described the system, it's a box. That should be enough. if you say that I'm expecting the particles to be in this configuration, you're effectively defining an additional set of walls inside the room. Well, who decided on those walls? This is that additional assumption. This is the additional information added. And we want to reduce those assumptions as much as possible. But what does it mean to be the minimal bias or the minimally assumed distribution? That's what we need to define. So that's where we're going. Okay, so we got tools for that, and so we're going to build up to that. All right, so motivation. Which distribution is more natural for these constraints up here? We've got a positive, so right now we're trying to model energy. So these perturbations, how much energy is available. So energy is always positive, or at least non-negative, and it has this fixed average. So I've got two candidates here. So I'm trying to move from this kind of cartoon example of the boxes to an actual distribution of microstates. So here, this is my energy axis here. Both distributions, this exponential distribution and this uniform distribution, have a mean that is the desired amount. Both of them are also non-negative. So both of these distributions meet the constraints that I'm given. They all describe non-negative quantities, non-negative outcomes that have an average of KB times T, KT. So somehow I need a way to say, is this more natural or this more natural? Does anybody have any thoughts about these two? Like, what do you think seems, just comparing these two, to be a more natural distribution? Why do you say that?
I think initially there'll be a lot of movement, and then once they space out, it'll be less spread.
Just keep in mind, so I'm not right now talking about, it's a good intuition, but the system I'm talking about isn't positions in a box. It's energy. It's energy in. So if we're considering these are all the microstates a chair can be in, then it's the energy of those. It's not the energy in the chair. This is the energy in the perturbations being applied to the chair.
So initially they're really, really close to each other. So there's a lot of energy because they're bumping into each other, and then over time they spread out, and then the energy reduces. And I think that'll be exponential. As they spread out more, there'll be less.
So that I think it'll be exponential. So where does the exponential in particular come from? Can we try to think quantitatively, not about your physical intuitions. Think mathematically about these two distributions, and what quantitative ways can we separate these two distributions? Yeah.
Think for the uniform, you need the two kind of the start and end point, right? To kind of say, oh, it has to fall between these bounds, and we also need to know what height it is, and the other one it can kind of just say what's the maximum and then the decay rate.
Okay, so there's a comment here about it's like the degrees of freedom that are tied up into the distribution itself. So there was a comment here that I drew this as being this wide, this uniform distribution. But there are other uniform distributions that have this mean. That could be this wide and it just would have a little higher density. It could be clustered right around there. It could be somewhere in between. So you can say something is uniformly distributed, but you then have to specify not just that it's uniformly distributed and it has a mean. You have to go a little bit farther and say the variance of the uniform distribution, the width of the uniform distribution. So the uniform distribution needs two parameters to fix the family, to fix the member of the family you're talking about. It needs a left boundary and a right boundary, which is equivalent to saying it needs a mean and a standard deviation. So it's a two-parameter distribution. you can still get it to have the mean, and it can meet those constraints, but it meets those constraints with two parameters. Now, the exponential distribution, it has infinite width. So it does decay, but theoretically, all energies up to infinity have some density associated with them. They are possible. So there seem to be more possibilities here. It's less constrained. And the way that plays out in math is that this is a one parameter distribution. And an exponential distribution, if you say it's an exponential, someone says, what's the average? That's all the information you need. So if you were to tell me that if I were to give you that constraint up there, that I just need to fix the average and everything's got to be non-negative, and you were to come back at me and say, all right, I'm going to use a uniform, I'm going to simulate that with a uniform distribution, then I'd say, okay, how are you going to implement that? And what do I mean? I say, which uniform distribution are you going to use? Of all the uniform distributions that have the mean, which is the only constraint I gave you, there are a bunch, like there is a degree of freedom that is left over that you as the programmer now need to specify. So if you choose this as if you're the programmer doing this stochastic simulation, and all you know is that you need this to be a constraint on your mean, and you choose this because you just know how to generate uniform distributions in code, then you have to then fix that other parameter. And you say, well, I guess I'll just make it go all the way from 0 to 2 KT. But that was a choice you made that introduced your bias. So this distribution reflects not only this constraint, but now your personal bias. And that's what we don't want when we're designing distributions that reflect data. So that's why we are more interested in the exponential for this problem. Because it's one parameter, you give me a mean that immediately fixes. There's only one exponential that goes with that average up there. And it feels better because now I'm not excluding these high energies arbitrarily. Like, here with this uniform, I've decided to include these energies, but you might have decided to do a uniform that looks like this, in which case you've excluded these energies. Here, we're not excluding any energies. It's granted that in order for this constraint to work, we had to make these ones have higher density than these ones, but it's still possible to reach all of these energies. Yeah.
Well, you still need to describe the curvature, like the eccentricity for the...
Not for an exponential. So in an exponential, this is all we need is that mean. Once you say it's an exponential, you give that mean, you're done. There are Weibull distributions and Erlang distributions and so on that are exponential-like that have a second parameter. If you would have chosen one of those, like that kind of brings up, if you would have come back to me and said, I'm deciding that my perturbations for my simulated annealer, I'm going to draw them from this ski slope looking distribution. It has infinite support, and I've tuned it to have the right average, but I've chosen a different slope here. So, this happens to be this is a Weibull distribution with a shape parameter of 0.1. So a Weibull distribution is an exponential-like distribution that actually degenerates into an exponential. It has two parameters. One of them is equivalent to the exponential rate, and the other one's a shape parameter, which allows you to drag the exponential down or up. And when you drag it up, it becomes more hump-shaped. And so, and you say, well, then how did you choose that shape parameter? He said, I just kind of thought 0.25 looked good. And so that shows you're introducing your own bias. Now, what we have to do is to justify that this is the best infinite support, infinite width distribution. That's what we're going to get to. But for now, I'm just trying to motivate that already, if it's just between these two distributions, this one should raise a red flag. Because when you implement it, there's a free variable that you, the programmer, have to populate just based on feelings, vibes. And we don't want to vibe code a maximum entropy distribution. So this is, again, our motivation. So both distributions have the right average. This one looks like it has more degrees of freedom. And this one definitely has fewer added assumptions. So how do we make this more rigorous? How do we say for sure that for these constraints, that is the best distribution, the least biased distribution? That's what we're doing. Any questions on this example so far? And we're adding more and more. Okay. All right, so more thought experiment here. Imagine that there are 1,000 possible microstates in our system. So I haven't fixed a macrostate. I'm going to talk about which macrostates we might be in, but the system could be molecules of air in the room. And there are different configurations. So I'm not saying there's 1,000 molecules. I'm saying there's 1,000 different position and momenta for each one of those, for the suite of those molecules. So for this room, this number is huge. It's much bigger than 1,000, right? Because every molecule could be in every position and can have a wide range of momenta, and all of those cross together, and so you get a really, really big number. So there's a lot of microstates, and they're not observable directly because the infinitesimal physical world is so numerous that we don't experience microstates. We experience coarse-grained macrostates. We experience the chair. We don't experience the molecular configurations of the chair that the chair is migrating through as it sits there in its own little chair. So, so that's the setup here. The microstate identities are not directly observable, but coarse properties are. So this refers to coarse graining. So what are some different coarse grainings, some different macrostates that we might observe? So imagine that the air is colored so we can see it, or imagine that you need air to breathe, and so if the air is not where you are, then you can't breathe, and so you can also observe it. So either way, it's possible to observe distributions of the air. So one of our macrostates is all air is in a 1 meter ball in a room corner. It's just over there in a ball of 1 meter. And that is a description of the system. Another description of the system, all air is on the left side of the room. So all air is over here, no air is over there. Another description is there's air everywhere, but there's a higher density over here than there. So it's thinner air than on the right side of the room than the left side. Or air is spread uniformly. So the density there is the same as the density there. Those are 4 different macro states, 4 different observable states of the room. Again, assume the air is kind of colored so that we know roughly where the air is, even though we can't identify a particular microstate. So when we think about those 4, then we say of the 1,000 possible microstate configurations, how many fall into each one of these macrostates? Which macrostate has more? Which macrostate has less? And if it helps, you can say, how much can you perturb each one of them and still be in that macrostate? So I've kind of motivated this in my little drawing of the little box with the 4 molecules in it, is that if all the air is in a corner of the room, if you get a little energetic perturbation and it takes one of those molecules and it moves it a meter away, then if that was in this radius of a meter and it was sort of out here, so it moves it a meter away, then now it's moved out of that microstate. So it was very easy to take the microstate take a microstate that is here and move it into another microstate that is not in the A macrostate. And that's where we're going to stop right now, is that to say it's just, so this sort of suggests that it's very exclusive to be in one of these configurations, because it's very easy to, when you're in one of these configurations, to get out of this configuration. So that kind of suggests that there are fewer ways to configure molecules in this room that fit into this description. There are fewer microstates that fit into this description. On the flip side, if air is spread uniformly over the room, if there's a certain distribution of molecules, you take one of those molecules and you move it a meter over here, just one molecule a meter over, I mean, that is a perturbation. That's a low energy perturbation. It could happen. But after you move that one molecule over there, it's still pretty much equal density everywhere. So it's when you're in one of these microstates, it takes a lot to move yourself into a microstate that doesn't fall into one of these categories. In fact, these are very common microstates. Yeah.
It's like, depends on how uniform is, right?
Yeah, so we have to define, there's kind of a chi-squared analysis you could do here or whatever, where you could say, is this uniform or not? And so you could say, can we statistically detect a deviation from uniformity? And here we're saying with, if I want to operationalize this, I can say with P less than 0.05 with a type 1 error of 5%, I cannot detect a deviation from uniformity. Again, use something like a chi-squared would be fine for that, or Smirnov, or your favorite distributional test. And then you could say, you could define that. And that would give you a large set of microstates, certainly much larger than this one. And it's my claim that there's a gradient here, where I would have fewer microstates fall into this description, a little bit more here, a little bit more here, and the most here. All right, do we buy that so far? Okay. Okay, so now knowing that, let's say I take you out of the room and I ask you, I say your grade in this class depends upon you getting this answer correct in one shot. You have one shot to answer this. I'm going to say, you've never entered the room. You know the description of the room. You know that the room has air in it. The room is shaped like this box. That's all you know. And I'm going to ask you, here are your 4 options. Which macrostate currently describes the room? Or in other words, the room has a microstate configuration at this instant of time. Which macrostate does that microstate fall into? Which one of these do you answer and why? Yeah.
E.
Why do you say D?
Because it's lower energy.
Lower, well, is there a more, so let's not worry about the physics. Let's just think about the math. Just think about the logic. Yeah.
It's the number of microstates for A is less than B, less than C, less than D.
Mm-hmm.
So D is greater than all A, B, and C, and that hence gives the highest chance of being correct.
Right, so the idea there, it's a great way to phrase that, is that if we assume all microstates are equiprobable, same probability of any microstate. So a microstate is a dart you throw at a dartboard. These are sizes of regions on the dartboard. And this region on the dartboard is gigantic. This is the bullseye. So if you just close your eyes and throw a dart at the dartboard, it's probably not going to hit the bullseye. But if you have a really large area around the bullseye taking up the whole rest of the dartboard, then it's much more likely you'll hit it instead. So if I don't give you any other information, then just go with the macrostate that has more microstates, because probabilistically, the system is just less likely to be in there based on the information I give. Does that make sense? So probabilistically, number of microstates tells you. Now we can think, this is getting a little bit more to the intuition from earlier. Let's say that I did, I had a pump or something like that. So I'm not going to get into all the details of this, but this is going to end up requiring energy to do this. But if I had a pump and I took all of the air and I compressed it and I put it into microstates that fit into that, I put it into that macrostate. So I compress everything up into that 1 meter ball in the corner. So if you do that, you shove it all into that A, and then it's going to have thermal agitation. So those things are just going to be jiggling around. So if it moves it momentarily out of A, so there's all of the molecules are inside that 1 meter ball, and one of those molecules moves outside of the 1 meter boundary through thermal agitation. Is it more, so if we think about it, it could get moved back in, like it could jiggle back in and then re-enter macrostate A. But if it's outside of that ball, there's going to be more ways for it to get farther away from that ball than to undo what it just did. So if we've got this ball up here in the corner and all of the other molecules are in here, and one of them happens to go over this boundary, we now are in a microstate configuration which is not in A. And this little molecule here, it might get jiggled right back and undo what it just did. But there are a lot more opportunities for it to go into additional microstates that aren't fitting A. And some of this comes from the numerosity argument as well. So, but if I instead said, let's say we started this in D, so we started in a uniformly spread case here, then most perturbations don't take me away from D. And those that do take me away from D momentarily, there's probably going to be more options to take me back into D than to stay away from D. So somehow D has a notion of stability, and A is somehow unstable. And what this tells us is that we should expect that over time, you're going to get a movement through a macrostate progression that moves toward macrostates with higher numbers of microstates in them. And that is an important law, which we'll formalize here in a second. But does that intuition make sense? That if we have descriptions of systems that are coarse graining, so there's multiple realizability, then the number of microstates that are equivalent to those descriptions gives us information about the probability that the system is going to be in those macrostates and how the system is going to move through macrostates and sort of what an equilibrium distribution will be. And what this is getting at here is that even through time, this maximal entropy idea ends up becoming a strong one. Because what we're saying here is that if you leave a system alone, it erases additional information. So if you push all of the air in the corner and you come in immediately after I do that, you see all the air in the corner, you say, oh, Ted was here. He loves pushing the air in. That is such a Ted thing to do. That's so Ted. It's giving Ted the air in the corner. But over time, the air will spread back out and it will spread through everywhere. And if you come back in an hour, you will come in and you have no idea that I was here. So that additional information that was added to the system beyond the constraints of the walls gradually gets erased over time. And that is going to be an important feature here too. The biases get erased over time. So that's a biased distribution. This is an unbiased distribution. Okay. All right, let's try to make that a little bit more formal. So how do we keep track of this? What is our bookkeeping mechanism for this? And this is a term called entropy. Sounds like a scary term, but it is just a count of microstates. So the entropy is a measure of the degrees of freedom or the number of microstates in a macrostate. So if a macrostate has W microstates in it, so I'm just assuming all the microstates are equal probable right now, then we can define entropy in two different ways, which are just scalings of each other. So we either define the information or the Shannon entropy as the base 2 logarithm of the number of microstates of that macrostate. And we use the units of bits for that. So this comes from information theory. This is our default in this class. Or if you're a physicist, you might use Boltzmann entropy, which instead of using the log 2 logarithm, it uses the natural logarithm. And by itself, the natural logarithm of the number of states has the unit of nats instead of bits. But the physicists like to scale it by the Boltzmann constant so that its units are joules per Kelvin. That's the kind of thermodynamics definition. And once we get through this, if you're interested, I can give you a concept for what it means to have a joules per Kelvin entropy. What do you mean joules per Kelvin? How does that have to do with anything? And that has to do with the amount of energy it takes to reduce entropy at a given temperature. But that's not important for us because temperature for us is just a plaything. It's not, we don't actually care about this Boltzmann constant stuff. So we're going to live in the information world, the H world. All right, so you might ask, why logarithm? It seems like count should be good enough. Why not just use W? And there's a very good practical reason for that. We use logarithms to make composition of two systems simpler. I've been talking about the microstates in this room, but this building has another room. Let's say it just has two rooms. So this is room A, and over there, whatever room 105, whatever that room is, that is room B. Now, if I want to talk about the number of microstates in this room, it might be 1,000. And then there might be 1,000 microstates in room 105 behind this wall. Now, if I want to talk about the number of microstates in the building, because these microstates are independent from those microstates on the other side of this wall, I have to multiply them together. So the number of different ways the building could be configured at a microscopic level is going to be the product of how many ways this room can be configured times how many ways that room can be configured. Well, it's not ideal in our system of science to have a quantity that when you add two things together in a system, that you have to multiply the quantities. And so you use the logarithm. So if I define the entropy of this room as the log of the number of microstates, and the entropy of that room is the log of how many microstates are in that room's macrostate, then when I want to talk about the entropy of the building, which is the composition of the two rooms, I just add the entropy of this room plus the entropy of that room. Because the entropy, the log of the product, is just the sum of the logs. And so that's why we use the log. It's just for convenience. It makes entropy look scarier, but entropy is really just counting microstates in a macrostate and then log scaling them for convenience. Any questions about this? Okay. All right, so in that 1,000 microstate room example, room A here, then as was kind of already diagrammed here, we can imagine that there's a an entropy ladder where the uniform distribution had more microstates. So we're going to say it has a higher entropy, and the clustered configuration had fewer microstates. So we're going to say it has lower entropy. And we expect systems to transition toward higher entropy macrostates. So more microstates, more common. And this is the second law of thermodynamics. So for an isolated system, so long as you don't open that door, for this room right here, if it just sits, then if you push all the air over there, that rare macrostate will very quickly disappear and will move into macrostates that have more microstates associated with them. That's the second law of thermodynamics. Or delta S is greater than or equal to 0. If you want to phrase it in the information sense, delta H is greater than or equal to 0. They're the same statement, they're just scaled. Entropy tends to increase. Now, what does that mean conceptually? We expect a system at equilibrium to be at max entropy. And so what is a max entropy distribution? This, actually this should be this macro state. So let me go and fix that. All right, this macro state erases all information or constraints from past macro states. So there are more constraints defining the rare states than there are the less rare states, is what we're saying here. So the least constrained version of the system is the equilibrium version of the system. The system moves towards the least constrained version. Nothing beyond the macrostate constraints can be assumed. So if I took you outside of this room and asked you, what macrostate is this room in? And all that I told you was the confines of the room, then you say, well, based on the information you told me, I'm expecting that all the particles to be uniformly distributed throughout the room. That's just based on what you told me. Now, if you give me another constraint, there's a fan spinning in the room, blowing that way. There's inside the room, somebody's taken all of the air and they put them into a balloon, and they put the balloon in that corner so it can't move outside the balloon. If you give me all of that other information, I will change my answer. But if you only give me the bounds of the room, it would be weird for me to suggest anything but the uniform distribution. And then at any given, again, this should be, I think I wanted this to be macrostate there. So what I'm trying to say here, no, this is good. So what I'm saying is that any given microstate is sort of the least predictable microstate. So it's if I was in a macrostate where everything was clustered into the room, it would be relatively easy for me to predict the microstates. Like there are a lot of microstates I could exclude, so there would be very few microstates that I would include in that. So if you told me that it was in macrostate A, then I would have high predictive ability on the microstate. But in the max entropy distribution, then every microstate is sort of, the distribution of microstates is kind of the least predictable. And so this is what we mean by the max entropy distribution is maximally disordered. Order is predictability. So there's some predictability, right? Like you know that the things can't go beyond the walls. But beyond the constraints of the room, otherwise you don't have any other information. So you just have to assume what's the least predictable way that things could be confined to this room. That's what it means to be the max entropy distribution. Are there questions about this, adding this kind of information flavor to it? Okay, so how do we apply entropy when microstates are not equally likely? So I mentioned that everything so far was based on the idea that every microstate, if there's W microstates, then there's a 1 over W probability that for each microstate. So that's how we defined this, where this is just the count of microstates and this is our entropy, is just the log of that. Well, this is equivalent to me saying, well, let's just divide those up into W's and then add W of them together. So I haven't changed anything. And then because this is a logarithm, I can take the reciprocal of what's inside, what's in the argument, and just put a negative out front. And so that I get this form. This form is identical to this form. But in this form, notice that what shows up in front of the log and inside the log's argument is the uniform probability of each microstate. So I can take this form and say, let's generalize that. And imagine that microstates have their own probabilities. So some microstates are more likely than others. And I get this formula. So in the discrete case, then I'm just taking this 1 over W, making it pi, and this 1 over W, making it pi, and this is identical to what we have up here. And so that's where we get the formula for entropy. In the continuous case, then it's very similar. I'm now integrating over a density function, but it's the same format. So the integral of the density times the log of the density, where x here is the microstate. It's the nuisance variable that you're integrating out over. So you integrate over all your microstates and you get this macrostate. So both of these can be phrased as expectations over distributions. So this, both of them are the expected value over your probability distribution or your density function of this quantity log of the probability. And that has a name we call surprise. So entropy is also referred to as the expected amount of surprise in a macrostate. And so what the second law tells us is that nature is maximizing surprise. When you open that door to see what the microstates are, you will be maximally surprised when you see those microstates, because it's in a very, the least predictable distribution, the maximally disordered distribution. You have no idea what the microstates are going to be aside from the constraints of the room. If you were in a different macrostate where everything was pushed up there, when you open that room, you would not be as surprised because there will be fewer options. So you can say, oh yeah, they're over in the corner. Well, you told me they were. So surprise. Now, so let's define surprise a little bit more. Surprise is, again, this quantity up here. It's minus log of the probability, which, if you're in the equal probability case, is just log of the number of microstates. So rare events are more surprising. That is a property that you get out of this. If outcomes are equally likely, surprise is the minimum number of bits to uniquely identify an outcome. So if there are W outcomes, like let's say there are 16 outcomes, then you need 4 bits to index which one of those 16 outcomes. So like if I have 2 states and they both have probability of 1/2, then I need a single bit. You can say, well, which state are you in? Are you in the one state or the other? So I need a 0 or 1. If I'm in 0, the system is in one of its states. 1, it's in the other state. There's only 2 states are equal probable. If I have a probability of 1/4, but 4 states, and they're equal probable, then of those 4 states, in order for me to communicate to you, this macrostate has 4 states, 4 microstates in it. Which microstates in it? Well, I need 2 bits in order to tell you which of those 4 states. It's either in the 0,0 state, the 0,1 state, the 1,0 state, or the 1,1 state, and so on. So if you're uniformly probable, then the surprise are the number of bits you need to index which of those states you're in. And so for the non-uniform case, then it's harder to define surprise at the microstate level. But you have to define average surprise at the entropy level. So for the non-uniform state, H is the average number of bits an optimal encoding would need to describe a microstate. So the idea here is that if some microstates are more common than others, like let's say that there's a macrostate that 99 times out of 100, it's in microstate 1. But then there's the rest of that 1 out of 100 times, it's in one of many, many, many other microstates. Well, if I want to communicate that to you, the first thing you would ask me is you'd say, is it in the common microstate? And I would just say, yeah, it's in the common one. And that would be it. You wouldn't need anything else. Now, in the rare cases where it'd be in one of the uncommon ones, I'd say no. And then you'd say, crap. Well, which one of the uncommon microstates is it in? Is it in the uncommon microstate that's colored whatever? And I'd say no. Is it in the uncommon microstate that's colored whatever? You would ask me more questions. And there is an optimal, it's a 20 questions game. And so if I were to average over for every microstate how many questions you needed to figure out which microstate you were in, that is what H is. It's the average surprise. And so then optimal encoding an optimal number of questions we need. So if you're at a high entropy macrostate, then that means that on average, I need lots of information to tell you what the microstate is. So if I know nothing more about this room, then there's boundaries of the walls and the ceilings and the floor. If you then ask me, well, where are all the particles? I'm going to need to tell you the position of every single particle and its momentum. That's a lot of information. That's a long list of information. But if I compressed everything into a tiny little ball here, then there are the list of information that I need to give you to tell you where everything is a lot less. So H somehow indexes the length of the list I need to give you to perfectly describe the microstate in that macrostate. So an increase in, and I said S here, but I'll change that to H to just be consistent. So use the light blue, increase in H. Is a decrease in knowledge about the system. So as time evolves, we lose information about systems. The universe is marching toward a state of high entropy. The heat death of the universe will be a state of the universe where if in some multiverse someone visits our universe, there will be no signs that we existed. It'll just look like a uniform room of air. You'll have no idea what activities went on before. So this room, you can, it's like you go to the beach, you play around with the sand, you like leave a message in the sand, that message over time erodes, and eventually just becomes a uniform beach again. And you have no idea that someone was there. That's what happens as entropy marches on. All right, questions about this. So this is how we define entropy. This is our meaning of surprise. It's a rough idea of where these numbers come from. And remember, this is all grounded in just counting microstates. Is that a question?
So high entropy, lots of information needed to communicate details of a particular microstate would be the air example would be this room has uniform distribution. We don't need much details for figuring out which macrostate it is in, but it has so many microstates. To figure out which one it is, we need more information. Is that how that looks?
That's right. The macrostate is minimally informative. So we know the macrostate, but it doesn't tell us a lot about the particular microstates. When you have a very informative macrostate, like all the air's in the corner, then suddenly the macrostate carries the description. It carries a lot more weight, and I don't need much additional information. So if it's critical for me to know, is the air, where is the air in this room? Where are the molecules in this room? If somebody says, well, it's a box, then well, that doesn't help me. That doesn't, but if they say, well, it's a box, but there's a fan that's blowing in this direction, or they give me more and more information, then that helps me say, okay, so it's probably, there might be a vacuum in that corner. So if I really need to get, if I need some reason to follow low density, then I can follow along that wall or whatever. But the highest entropy macrostate carries the least amount of information about the microstates. And that's beautiful from a machine learning sense. That is what we want. To be good programmers, we need to understand that. To be good statisticians, we need to understand. Okay. All right, so least bias distributions. Let's get into this idea here. So getting toward the machine learning, toward the optimization. So a max entropy distribution, like I've been saying, it's this least biased distribution. The amount of entropy lost by using another distribution is a measure of the information added beyond the system description. So if I were to measure the entropy of uniformity, and it came out to 100 bits, and then I were to measure the entropy of compressed into the corner, and it came out to 46 bits, then that would tell me that there were 54 bits of added assumptions from beyond just the shape of the room. So you take the shape of the room, and then you keep adding additional constraints, additional assumptions. You can ask how much information is in those additional assumptions, and it's the difference in the entropy of the uniform macrostate versus the macrostate that we're comparing to. So we want to reduce those to zero. We want to make sure that the only thing our macrostate reflects are the constraints that our stakeholder has given us about the system. So, so the idea here is that when given constraints, the most principal choice as statisticians, as programmers, as modelers, is the description that has the maximal entropy distribution. It minimizes arbitrary bias. If I'm designing little perturbations of my searcher, then I don't want to just choose an arbitrary perturbation that I think looks good, that I think, oh, I'm just going to uniformly, I'm never going to go more than one in that direction or one in that direction, and that's my search. Well, then someone can ask you, well, why one? Why not half? Why not 1.5? These are things that I'm choosing, and I'm adding constraints to the system. So if all the hyperparameters say is that the average jump should be no more than 1, then I need the maximal entropy jump that averages 1, but otherwise doesn't add any other information. That is the MaxEnt distribution, minimizes this arbitrary bias. So now that we have a formula for entropy, we can solve for these distributions. So in the continuous case, you have to use something called calculus of variations to solve for distributions. Outside the scope of this class, but if you ever wanted to solve for a MaxEnt distribution over a continuous random variable, the math is there. It's not hard. It's just a little beyond what you get in a typical calculus or real analysis class. But Lagrange multipliers, that's something that if you look up constrained optimization, this is something that a lot of people, especially for operation research, you take an optimization course, you're probably going to learn about constrained optimization. That looks a lot more like normal optimization or normal calculus. But the point is, it's outside the scope of this class to be able to do this math, but the point is that the math exists. And so you can set up a problem like this one. You can say maximize entropy H, subject to the constraint that all the probabilities in my distribution, this is the discrete case, sum to 1, and all the probabilities are greater or equal to 0. And ... that's the additional system constraints added. So that's where you say, and I want the average value to be a particular set. Or you can add all of those things here. I want whatever additional system information you have there. And through the magic of Lagrange multipliers, there is a method that will give you the probabilities, PI, for every one of your discrete microstates that maximizes entropy. And that's the distribution that you should use. So I've got a little demo of this. This MaxEnt demo here. So this was, I guess I'll do the language model here first. So this got a lot of traction in early days of natural language processing. So I have a bunch of words. So up here, river. A river is it's a noun, and so it's a nature word and it's a noun. Forest is a nature word and a noun, but it's also long. So every word has got some properties. Some words have no properties. So if I then look at a language, I can say how often do these words show up. So like river, I said it showed up. I saw it in a text. River showed up once there. And so that now tells me that nouns are frequent in this language. I mean, I only have one. But, and so it then down here, this is the maximal entropy distribution subject to the constraint that nouns have a particular frequency. And notice that it promoted all the nouns. If I then say, okay, river is actually pretty frequent, but there's also forest has shown up here. Well, so now I see that river is the frequent noun. Forest is also a noun, but it's long. And so what I'm seeing here is that if I make that, forest a little bit more here, then it's I can't highlight, but this long word that's not a noun has now increased in probability to 0.1%. So what I'm seeing here is that of all of the words that are in this language, I can say, what is the average number of nouns? What is the average number of long words? And so on. Each one of these are constraints. So I want a distribution over all words that maintains these constraints that are statistically consistent with what I've already seen in the language. And this will tell me, based on this distribution here, so 23.8%, 28.5%, and so on, that based on this distribution, if I want to choose, say, the next word in a sentence, then this gives me a distribution of what I should choose. I should never choose these words that are not nouns, that are not anything, because those type of words never show up in the language. So I'm building macrostates out of these coarse-grained properties. The number of nouns, the average frequency of nouns, the average frequency of nature words, the average frequency of long words. And those become constraints on a macrostate. The microstates are then the probability of which word actually shows up. And by maximizing the entropy of that distribution, I get the least biased guess of the most appropriate word for this context. And this is how some of the earliest prediction algorithms, I mean, now we have all these other ways to do it, but this is where MaxEnt really became very popular as a natural language processing. Now, the ecologists have taken over, and they use this a lot. So here I've got a spatial distribution, so latitude and longitude. And so there are properties like here's an elevational map, and here is a temperature map, and here is a moisture map. So those are all different maps. And so I can now say, if I can tap on one of these areas and say, I found a species here. And I also found that species here. And I also found that species here. And over time, as I start putting where I found the species, it then creates a macrostate that's constrained by the statistics across these features. So it's saying that of the species I found, it's more common to be at certain elevations, like the average elevation was this, the average temperature was this, the average moisture is this, of all the ones I've seen so far. That then defines a macrostate, and I can maximize the entropy of locations within that macrostate. And it gives me a prediction of, oh, well, you know, if you wanted to search for another case of that species, you should probably not go here. Maybe you should look up here. And this works remarkably well. People do this with whales in the ocean. They do this all sorts of, they do archaeology now. People will dig up an artifact, like a bowl from the 5th century, and they'll find another one and another one. And they put them into these MaxEnt distributions that have all of these features down here. And then they say, we only have a limited budget to dig. Where should we dig next? The MaxEnt distribution tells them, oh, you should probably dig here next. This is the most likely place based on the observable features in macrostate. Based on what you can observe, based on the stats, this is the most likely place that you're going to find the next artifact. And it works remarkably well. Are questions about that? Say of MaxEnt. Or what? Actually, maybe I should say, it's 11:45. This is a good place to stop. This is about where we were going to stop anyway. If you have questions, happy to take them after here. But what we're going to do here is we're going to now use MaxEnt to answer the question of what's the best distribution of energy perturbations. And then that is going to, for one, it's going to allow us to define this soft max thing you may have heard about in machine learning. And then it will then allow us to keep moving. We'll talk about Monte Carlo sampling, and eventually we'll get back to simulated. All right, that's all I got for you. So we'll see you Thursday.